All right, this is number 2 from section 1.9. Let's read the instructions. It says, assume that T is a linear transformation. Find the standard matrix of T first. And they also give us a condition on T. Notice that T goes from R2 to R2 and it rotates points about the origin negative 4 pi over 3 radians. All right, so you might recall that when you rotate things about the origin, this is in the positive direction and this is in the negative direction. So the fact that that's a negative angle means we're rotating in the negative direction, which looks like clockwise. All right, but it's supposed to rotate everything 4 pi over 3 radians clockwise. So that sounds a little bit tricky. Okay. Now, you might recall that one of the theorems from the material says if T is a linear transformation, then you can always write T as some matrix times column vector X. All right, and we call this the standard matrix. So there always exists a standard matrix whenever T is a linear transformation, okay? So in this case, we have to find that standard matrix. And you might also recall from the lecture notes, maybe the PowerPoints or some of the videos, that the standard matrix can always be written like this. Okay, now this is the image of the first column of the n by n identity matrix. Okay, so that would be something like 1, 0, 0. This is the second column of the identity matrix. So that might be something like 0, 1, 0. So you just take the images of all those columns of the identity matrix. And I'm assuming that we're going from Rn to Rm in general. All right. So you really will have n columns to consider. But that's how you get the standard matrix in general. Okay. So in this particular case, they tell us that T is going from R2 to R2. All right. So to find the standard matrix, we just have to consider the identity matrix in R2, which remember looks like this. And we just have to find the images of the first column of the identity matrix, and then we have to find the image of the second column of the identity matrix. And those two 2-by-1 matrices will form the standard matrix A. So we just have to find these two images, all right, under this particular transformation. So let's see if we can do that given the conditions in the problem. And this is a little bit tricky, but here's my XY plane. We are in R2. Okay. So we're looking for the image of 1, 0, and that is a point. It's right here. And we're just trying to figure out where 1, 0 goes to, essentially, in this transformation. But just remember, they tell us in the problem that we're rotating this thing negative 4 pi over 3 radians. So that means we're going in the clockwise direction, 4 pi over 3. Okay. All right, now let me try to rotate that point 4 pi over 3 radians in this clockwise direction. Well, if I'm going in this direction, this is pi radians. Okay, I'm going to make that a little darker so you can see it. But that's pi radians right there. 4 pi over 3 is a little bit more than pi. In fact, it's pi over 3 radians more than pi. So it's going to get rotated to that terminal side, where this is pi over 3 radians. Okay. Now, just keep in mind, it's still going to be 1 unit away from the origin. So that point is still 1 unit away from the origin. So the length of this hypotenuse is 1. Okay. Now let's just try to find the coordinates of that point from that little picture. And I'll try to resketch it a little bit more clearly. So here's the triangle. This is pi over 3 radians. We're looking for the coordinates of this point. And the length of that hypotenuse is 1, because we know that the point still has to be 1 unit away from the origin. All right, so what is x and what is y? If we can find that x and that y, we'll have this right here. It'll be the coordinates of the image of that rotation. Okay. Well, you might remember in general, r cosine theta is the x-coordinate if you rotate, if your hypotenuse is r radians and your angle is theta. So in this particular case, x is going to be 1 cosine pi over 3, at least in absolute value. We have to be a little bit careful. Since we are in the second quadrant, I need to make that a negative. So I'm using a little bit of trig here. But that's really negative cosine 60, because you might remember that pi over 3 is 60 degrees. Pi over 6 is 30. I know sine of 30 is 1/2, so that means cosine of 60 is also 1/2. So it looks to me like the x-coordinate of that point is a negative 1/2. All right. So I can actually put that up here if I want to. That is the x-coordinate of that image. But what about the y-coordinate? Well, it's just r sine theta, or in this case, 1 times sine pi over 3. Okay. And, well, that's sine 60. And notice, by the way, the y is positive, so I don't have to worry about the sine. I'm in the second quadrant. But I know sine of 30 is 1/2, so sine of 60 is square root of 3 over 2. Looks like the y-coordinate is square root of 3 over 2. So that's this guy right here. All right. You know, there is a way to do this for an arbitrary theta and then go back and plug in the pi over 3 or the negative 4 pi over 3 later. But I'm just kind of assuming that theta is equal to negative 4 pi over 3 right away. So that gives us the first column of the standard matrix, A. Now we need the second one, which is the image of 0, 1. So let's see if we can figure that out. So we're looking for the image of 0, 1, and there's 0, 1 right there. So what happens to 0, 1 when we rotate this thing clockwise 4 pi over 3 radians? Well, right there, that's just pi. 4 pi over 3 is going to be a little bit further than that. It's going to give me a pi over 3 right there. It's still going to be 1 unit away from the origin, so that's 1 right there. So I just have to figure out the x and the y for this particular case. So once again, I'm probably going to need to use a little bit of trig. Okay. Well, if this is pi over 3, that's got to be 90 minus pi over 3, or really pi over 2 minus pi over 3. Kind of an involved problem, really. So that's 3 pi over 6 minus 2 pi over 6. That's just pi over 6. So it looks like the angle there, the acute angle, is pi over 6. All right. So once again, let's use our relationship, which says that the x is r cosine theta. So here my x is going to be 1 cosine pi over 6. But that's the same thing as cosine of 30, which is square root of 3 over 2. But let's be careful about the signs. Notice the x is negative here because we're in the third quadrant. So I better make that a negative. All right. So remember, right now we're looking for the image of 0, 1. And I just found the first coordinate, negative square root of 3 over 2. All right. Now let's find the y-coordinate. That's just going to be r sine theta, or 1 times sine of pi over 6. But once again, we're in the third quadrant, so I better be careful to make that a negative. Okay. And that's the same thing as sine 30. That's negative 1/2. So I just found the image of the second column of the identity matrix in R2. So remember what we said. A is just the image of the first column. That's the first column of the standard matrix. And the second column is the image of the second column of the identity matrix in R2. So we're almost there. So if you go back to the work that we did before, we already found the image of the first column is negative 1/2 square root of 3 over 2. And we just found the image of the second column is negative square root of 3 over 2, and then negative 1/2. All right? So that should be your standard matrix. So anytime you multiply this by an arbitrary point, x, y, it's going to rotate it 4 pi over 3 radians in the clockwise direction. So this is your answer.